Okay, in today's lecture, as part of the recent topics in biomaterials, I will be discussing the biophysical aspects of cell material interaction, analytical and experimental results. So, essentially I will be dealing with the influence of external field on the cell material interaction, and first few external field influence. So, in first few slides I will be mostly dealing with how the electric field will essentially influence the cell material interaction, and then it will be followed by series of experimental results where I will be showing that how the external magnetic field can potentially induce antibacterial or antimicrobial property in materials. So, this biophysical interaction is essentially it is at the crossroad of biological science, material science and physics. So, certain physical aspects like electricity and magnetism, those kind of aspects is important to understand this biophysical interaction, and we will be also dealing with the material science aspect. Essentially material science aspect means like all the materials, they will not exhibit significant influence in the presence of electric field unless they have some piezoelectric properties, or because if they are perfectly insulator, it may be possible that they do not show or they do not exhibit good biophysical interaction, and of course biological science is involved in this kind of biophysical interaction. Now, origin of bioelectricity, essentially there are two school of theories. One school of theory is the diffusion theory, which states that chlorine ions dissociated from sodium chloride in water may move at a faster rate than its sodium plus counterpart, and therefore it provides a negative charge. What it means that in the chlorine ions, which is also available in large quantity in blood and other body plasma, as well as sodium plus ions. So, this diffusion theory states that if chlorine ions they move faster than sodium plus ions, in other words if anions move faster than cations, then essentially that will lead to a net negative charge, and that is what the concept of this diffusion theory, and that is kind of one school of theory which supports the bioelectricity. The other school of theory is that membrane theory, which claims that a membrane which possesses selective pores permeable to one type of ions separate ions of different charge. Now, here one must remember that cell as such it is enclosed by a lipid bilayer, and then each organelle, for example mitochondria or even the nucleus, they will also enclosed by a bilayer. So, essentially this bilayer they are not like a completely tight membrane, they also contains pores, and these pores are of different sizes. So, essentially membrane theory states that if these porous membranes or the pores in the membranes, if they selectively allow the movement of cations for example, or movement of anions for example, then what will happen, one side of the membrane there will be net positive charge and other side of the membrane there will be net negative charge. So, because of this charge separation, that will also lead to the bioelectricity net bioelectricity effect. So, there are two theories, one theory depends on the kinetic aspect of the movement of the cations and anions, and other theory is more related to the membrane theory, which is related to the transport of anions or cations through the membrane, and these membranes are this basically the cell membrane or nuclear membrane, etc., etc. Now, this other things is that now there are some literature reports which also states that that this electric field they are distributed in and around quiescent and dividing cells. So, that means when cells are undergoing mitosis or cytokinosis and mitosis, around that time, if for example, if you look at here now, if there is a field of alternating directions like AC current is flowing in these directions, then what will happen, there will in that AC current there will be some positive ions and negative ions also will be moving in particular direction. So, it shows that unidirectional net force acting on the dipole and unidirectional net force acting on the charges like which are either positive charge or negative charge. So, if the situation will arise such that the net charge positive charges or net negative charges will be higher at one side compared to the dipose, then that will also lead to the bioelectricity. And in the topmost part, it is shown that that if the positive or negative cations or anions, if their movement is also influenced by the AC current directions, then that will also lead to a non-uniform electric field distribution around the cells. Now, this electric field influence also depends on the intensity, electric field intensity, as well as the exposure time. Now, for the same type of cells, people have shown that if you apply a certain magnitude of the electric field, then it will assist in faster cell division process. But if you apply the different magnitude of the electric field, for example, after 30 minutes and after 50 minutes, here after 30 minutes, after 60 minutes, like different types of cells, same electric field magnitude, that can cause programmed cell death or cell apoptosis. So, what is the major message is that electric field influence on cell division or electric field influence on cellular functionality is largely dependent on the cell type. So, if it will have some influence on the particular cell type, for example, if it will arrest cell proliferation or it will cause cell division, at the same type that same electric field magnitude or the same magnitude of the electric field can cause complete cell destruction or cell apoptosis. And this kind of cell apoptosis will be very good for the cancer cell treatment, because cancer is essentially uncontrolled way of cell division, and by any chance that these cancerous cells that can be killed, that means this uncontrolled cell growth can be reduced, and therefore, that will give benefit to the cancer patients. Now, what we have tried to do recently, like we tried to understand that how an individual biological cell, if it is placed in an electric field, the electric field means between positive electrode and negative electrode, how it will respond to the electric field. Now, to solve this problem analytically, we have made some assumptions. First assumption is that this is a near spherical nature of the cell and the nucleus, and then second one is that resistivity of the cytoplasm and nucleoplasm are considered to be the same. So, there is no difference in the resistivity. Then we have considered the cytoplasm and nucleoplasm as the resistor, cell membrane and nuclear membrane as a capacitor. And then third assumption is that capacitance per unit area of the cell membrane and nuclear membrane are the same. Then fourth problem is that although it is widely known that a living biological cell, they contains a number of organelles, for example, Golgi body, mitochondria, ribosome and so on. For the sake of simplicity of the model, we have only considered the presence of nucleus, not any other organelles. Fifth one is that conductivity of the cell and nuclear membrane is neglected. The last assumption that was made in this analytical problem is that conductivity of the cell and nuclear membrane is neglected. So, based on these assumptions, we have attempted to solve this problem to understand that how a biological cell would respond to the electric field. Now, here in this view graph, what is shown that this is a cell membrane which is a capacitor, this is a cytoplasm which is a resistor, this is a nuclear membrane which is a capacitor, this is a nucleoplasm which is a resistor. Now, when a current will pass through this dotted line which is shown, this current can bypass the nucleoplasm and then still it can go through the cytoplasm and go to the ECM. So, from one end of the cytoplasm it can go to the other end of the cytoplasm, finally it will go to the ECM, extracellular matrix, or the current can pass directly through the cytoplasm and nucleoplasm and go to the other part of the cytoplasm and finally get out of the cell to go to the extracellular matrix. Now, whether the current will pass directly through the ECM not entering the cells, that is case 1, case 2 whether current will pass only through cytoplasm, case 3 the current will pass through cytoplasm then go to nucleoplasm and go to cytoplasm, that is case 3. For all these 3 cases, one can construct the resistance capacitance circuits and then one can apply the Kirchhoff's law at different nodes here and try to solve these equations to find out that what will be the time constant for this RC circuit. Now, We have solved these analytical problems, and here you can see that there is resistance and capacitance parameters. So, Cn is the capacitance of the nuclear membrane, and this is the Rn is the resistance of the nucleoplasm. Rc2 is the resistance of the cytoplasm, your Cm is the resistance of the capacitance of the cell membrane, Rc1 and Rc3 is the spatial value, the spatial dependent of the cytoplasm resistance. So, this is Rc1, let us say, this is the Rc2 resistance here, and this is the Rc3 resistance. Now, if you solve the multiple equations, then you finally get to the analytical equations which has some form like Ax square Bx plus C is equal to 0. So, x has two roots, and this x is actually tau 1 and tau 2, that is the interaction constant or the time constant value for this biological electrical analog of the biological cell, that circuit. And then what you can see here, that if you know all the capacitance values and all the resistance values in this equation, then you can essentially find out the value of the tau 1 and tau 2, and depending on whether you get this Schonbach model or our own model, you can get this tau 1 tau 2 value. These values are from the textbooks. Now, from a standard textbook we have taken this value for a biological cell, and we have found out the resistance of the cytoplasm. You can find out that R is equal to rho into L by A, and from that you can find out that what is the resistance Rc1, Rc2, Rc3, it is of the order of kilo ohm, and then resistance of the nucleoplasm is 174, that has been also taken from a standard textbook. Now, capacitance of the membrane and capacitance of the nuclear membrane, that is also 10 to the minus 11 farad, and from that what we have found out that this tau 1 and tau 2 values is around 1.55 to 3.26 microseconds. So, that means it is a very low fraction of a second, and here what you can see that same tau 1 and tau 2 value is 1.7 to 4.9 microsecond. So, what it essentially tells you that this tau value is less than 10 microsecond. So, it is roughly tau is somewhere at around 1 to 5 microsecond. So, that means that if a individual biological cell, if it is placed in an electric field, then it will respond to that electric field within less than 10 microseconds. So, which is a very small time scale. And however, such scenario will be different if multiple such cells are placed in the ECM, and then they are considered between this positive and negative electrode, and then similar way if you consider that current will flow through all these individual cells, then that case this time constant value may not be less than 10 microsecond. We have not solved this kind of problem, but there are opportunities that one can trying to solve these multiple cells in the ECM and trying to adopt the same kind of strategy to find, or similar strategy to find out that what will be the tau value for the capital N number of cells when they are placed in an extracellular matrix. Now, second approach what we have done, that is that how this tau value changes with the cell size. Now, how tau value changes with the cell size, that means that R value. Now, if you remember that I have already taught you earlier that there are 4 cellular adaptation processes. Cellular adaptation means when a cell is placed or when cell experiences the particular external damage kind of scenario. Coming to that influence of the cell size on the interaction time constant. Now, if you remember it correctly, that there are several ways that a biological cell can adapt to a changing external environment, what is known as cellular adaptation process. Now, there are 4 types of cellular adaptation process. One is atrophy, one is hypertrophy. So, depending on whether cells will decrease its size or cells will increase its size, essentially that term, the biological term that is used to describe such situation is known as atrophy or hypertrophy. Now, and the cells can do it because cells have very much elastic like properties, and therefore, cells can increase its size or decrease in size. So, therefore, the changing cell size should in principle have an influence on the time interaction time constant, what we have evaluated following this typical electrical analog of single biological cell. Now, this slide tells you that if there are tau 1 and tau 2, these two values that we can get from these equations, earlier equations, and then if you vary the Rn by R0 value, Rn is the radius of the nucleus and R0 is the radius of the cell. Now, if you vary this ratio of the radius of the nucleus and radius of the cell with, let us say, from 0.2 to 0.8, now depending on the value of this or independent of this value of this ratio Rn by R0, the time constant will monotonically increase with increase in the R0 value, and what you have seen here, that is in the 10 to the minus 5 meter, so close to micrometer range, and in this range of the increasing in the size of the cells and depending on the variable, that is Rn by R0 ratio, the time constant essentially increases with increase in the overall cell size. The other important variable in this analysis is the capacitance. Now, if you change the capacitance of the nucleus or nuclear membrane, or if you change the capacitance of the cell membrane, in both the cases or in model 1, let us say, what you see, there is a steep increase in the time constant with the capacitance values. So, whether the Cn increases or the Cm increases, tau is bound to increase. But what you see here, that influence of Cn on the increase in tau is much more drastic or much more rapid, because the slope is much higher compared to the slope of that tau versus kappa Cm. Okay. So, accordingly, what you can say here, that Cn, the capacitance of the nuclear membrane, will have much more marked effect on the time constant of this biological cell. And what we believe, that nuclear membrane traditionally is a bilayer structure, and there is a called nuclear pore complex, and through this nuclear pore complex will assist much more flow of the ions, or according to the membrane theory leads to the more bioelectricity. Now, increase in the capacitance of the nuclear membrane essentially means you are thinking of that spacing between the two membrane, that which constitute the nuclear membrane and the structure, and we believe that possibly that causes the change in the interaction time constant. Now, what we have done, we have designed and fabricated a pulse electric field generator, and with which one can apply different magnitude of the voltage, and in the first case we have applied that 1 voltage, and then we have frequency we have fixed at 100 hertz. Now, duration, what we have done, that we have first incubated the cells in contact with materials for 12 hours, then we give the shock for 5 minutes, and then we let the cells incubate for another 6 hours, then give the shock for 5 minutes electrical shock, and then we let the cells to incubate or proliferate on the material cells for another 6 hours. So, total 24-hour cycle, and in between there are 10 minutes of the electrical field treatment. Now, this is like 8 well plate, and you can see this is the cell culture solution, and this white stuff are samples. Now, two type of samples we have used. One is the pure hydroxyapatite, because hydroxyapatite is considered as bioactive and biocompatible material, and the another set of samples that we have used have barium titanate. So, we have added the 40% barium titanate, because thinking that the addition of barium titanate will increase or will induce the piezoelectric properties in the HAP, which is otherwise a perfect insulator. Now, with the addition of the piezoelectric HAP of barium titanate phase, we can increase the piezoelectric strain coefficient and so on. So, thereby we can study the materials aspect of this electric field influence experiments. Now, we have used that standard protocol for this incubating the L929 cells, and then what we have done, that we have constructed two type of conditions. One is a parallel electric field and one is a perpendicular electric field. So, parallel electric field, what we have seen, that in case of the parallel electric field, we apply the 1 volt field and 100 hertz, and duty cycle is 6%. So, here the electrodes are parallel to that well plate wall, and then we have put the samples here. So, one end is positive, one end is negative, and then current is field is applied externally, and in the vertical perpendicular electric field what we have done, that is top is the positive electrode and the bottom of the cell wall is a negative one, and then we have connected, we applied the field, and then again the similar parameters were used. Now, what we see here, that in case of the without electric field pure hydroxyapatite and have 40% barium titanate. So, these are the L929 cells, that is mouse fibroblast cells which are seeded on these two samples. So, this is without electric field 24-hour culture, this is with electric field 24-hour after 24-hour culture, but with 10 minutes of the electric shock. Now, from a visual inspection of these two surfaces for individual material, HAP and barium titanate, HAP without electric field and with electric field, and HAP barium titanate without electric field and with electric field, one can clearly see that more number of cells are proliferating in the presence of the electric field. Therefore, the field effect is pronounced irrespective of whether it is a hydroxyapatite or hydroxide barium titanate composite. Now, we have done some MTT analysis trying to see that how this influence it is quantitatively. Now, this is for the control sample, the hatched one is that with electric field, unhatched is the without electric field. Now, what you see here, that this star is actually p less than 0.05, and then what you see here after post hoc analysis we find that for both HAP and HAP barium titanate, that mean OD values after applying the electric field is statistically significant compared to the absence of the electric field. What it makes us to believe that if you apply the electric field, then one can essentially enhance the cell proliferation, particularly the L929 cells on these two materials HAP and HAP 40% barium titanate. Now, further experiments are in progress trying to see that whether you can optimize the electric field or you can optimize the electric field application sequence, in what way you can enhance the more cellular functionality on these electrically treated surfaces. And the final aim is that if we are able to optimize or if you are able to enhance significantly the cellular proliferation on these two electric field treated surface, then ex vivo tissue formation is possible, and such ex vivo tissue formation prior to the implantation in the human or animal would be helpful for osseointegration of these materials inside the in vivo environment. So, that was the ultimate goal. Now, in next few minutes what I will show you, I will show that we have also designed and developed a magnetometer, electromagnet, and that electromagnet that is based on the simple physics principle, and we have put a slot here, and through this slot one can put the 6 well or 8 well plates inside the magnetic field. So, this is called the sample window, and this is your front panel view of this electromagnet. Now, by changing the turn or you can by passing the different field, one can get up to 1000 Gausses or 0.1 Tesla field, 1 Tesla 0.1 Tesla magnetic field one can achieve with this electromagnet. Okay. Now, there are different effects. This is the kind of table shows the summary of the major effects of magnetic fields on different cell types. Now, what it says is that if you apply static 10 Tesla magnetic field on the human fetal lung fibroblast cells, there is no effects on proliferation. Now, if we apply the 5 Tesla field on the E. coli bacteria, no mutagenic effect. If you apply 7 Tesla field for the human tumor cells, inhibit cell growth, and if it inhibits cell growth, that is quite good. So, what you see from the major message from this slide is that depending on the magnetic field strength as well as the cell type, the influence, the effect is also variable, like either you have no effect on the cell proliferation, or it can inhibit the cell proliferation, or it can orient the cells also. For example, when we apply the static field of 10 Tesla, cells are oriented perpendicular to the direction of the magnetic field. However, not such any specific orientation pattern is found when it is cultured in absence of collagen. So, what it says that human A172 cell lines, when it is embedded in collagen gels, then cells are oriented, but when it is embedded without any collagen, then there is no specific orientation. So, it is not clear whether the magnetic field can or magnetic field has the potential to orient the cells in a particular direction. It also depends on the micro environment or environment just outside the cell. So, if you spread the collagen on the surface, then there is a potential that this collagen containing on the material surface, the cells can have some orientation. Now, these are like other literature reports where it says that when you apply the static 14 Tesla field and on the muscle cell assemblies, there is changes in morphologies and cell colonies are extended along the direction of the magnetic field. So, when you do similar type of test on Mg63, that is osteosarcoma cell lines, it increases the ALP activity, that is alkaline phosphatase activity, and also ECM, that extracellular matrix release, and at the same time if you apply 24 hours, that is a reduction in proliferation or growth factor. So, again I repeat, depending on the magnetic field strength, depending on the cell type as well as the exposure time, which is typically varies from 1 hour to 7 days, that effect is also very different. Now, this effect is also equally different in case of the bacterial cells. So, earlier all those two tables were shown, those were for mammalian cell types. For bacterial cell type, most of the experiments are carried out in that E. coli bacteria, that is the gram negative Escherichia coli bacteria. Some are also carried out on the Pseudomonas species, and this essentially again this kind of field which was applied like 7 Tesla or it varies sometimes up to 10 Tesla. The exposure time was 12 hour, 14 hour or less than 30 minutes. What you see when you treat it for 12 hours, there is decline in cell number, and that is good because you want much less number of bacterial cells to proliferate, so that chances of infection will be less. Now, when you apply this 1.5 millitesla, that probably this magnetic field strength is quite low. Even after application for 24 hours, there is no obvious difference were found between the test and control samples for all the bacterial species. Now, when you apply for less than 30 minutes, there is an exponential decrease with magnetic field and number of CFU increases. CFU means colony forming unit for the bacterial cells will increase with time of exposure. So, similarly, if you apply the 50 Hz and 2.7 to 10 millitesla for 0 to 12 minutes, that ability to form colonies decreased with increasing magnetic field. So, either that colony forming units decreased or they decreased with increasing magnetic field and time exposure, or there is no change in bacterial morphology. That is what has been observed for E. coli, that is 50 Hz and 10 millitesla field. Now, possible mechanisms is that magnetic fields may induce active oxygen formation, and these radical reactions with this paramagnetic ion and oxygen are affected by this magnetic field, and the mechanism of the effect of magnetic field may be different in gram positive and gram negative bacteria. So, that is the reason when we have started investigating this particular aspect, we started with first gram negative bacteria, that is E. coli bacteria, which is widely investigated, and in the next stage we are trying to find out similar influence on the gram positive bacteria, for example Staphylococcus epidermidis or Staphylococcus aureus species. Now, there is also possible effect of the electromagnetic field on the permeability of the ionic channels in the membrane or the formation of the free radicals due to the magnetic field. So, these are like possible mechanisms. Now, these are the design of this magnetic field. You can see that is the 17 millimeter, that is the distance through which these samples, that 8 well plates or 12 well plates, they are introduced in this magnetic field. This is the where the electrical coil things are there. Depending on the turns, depending on the amount of current that you are passing through this coil, you can get the magnetic field using, that is quite clear from the basic physics aspect. Now, initially we have done this test up to 150 Tesla, and then we are increasing the field to 100 millitesla. Magnetic field exposure duration is varied from 0.25 hours to 4 hours, and we have done this first use the sample control disk, and then we also use the bacterial strain, that is E. coli strain from ATCC. We have followed the standard protocol for the bacteria culture, and after the standard protocol we use the scanning electron microscope to observe this bacterial cell morphology. Now, this is what happens when you apply the 50 millitesla field and 30 minutes of the exposure. Without magnetic field, you can see that so many number of bacteria they are adhering very happily. With magnetic field like 0.5 Tesla, you can see number of bacteria is reduced, and also both at high magnification you do not see that many number of bacteria or that many number of colonies on the control disk. Now, similar observation has been made when you increase the magnetic field to 100 millitesla and exposure time is kept at 0.5 hours, that is 30 minutes. Now, what we see here in the control sample, again the number of bacteria is less if you see that 50 millitesla, and if you see that 100 millitesla, certainly the increasing the magnetic field has a positive effect as far as the reduction in the number of bacteria cells are concerned. We have also done similar experiments on pure hydroxyapatite, because if you remember correctly that hydroxyapatite is one of the material which is widely regarded as excellent biocompatible bioactive material, but there are two issues of hydroxyapatite, and one of the issues is that lack of bactericidal property. So, therefore, we try to investigate whether if you apply the magnetic field, whether you can induce antimicrobial property in the hydroxyapatite, and we have demonstrated that when we apply the 100 millitesla field, you can essentially reduce largely or significantly the number of bacteria those are seeded on this hydroxyapatite surface. This is like relatively high magnification ACM image, essentially showing the possibility of there are possibility that there are cell membrane are distracted, intercellular elements are coming out, and what we can see that what we can possibly see that individual bacterial cells they have their cell membranes are distracted, intercellular elements are coming out of the bacterial cells, and therefore, it causes the death of the bacteria. So, however, we are still looking into the possible mechanism of the bacterial cell death. So, I think I will stop here, and then we will start with the different topic in the next lecture.